Welcome to the Operations Research video lecture. We are now on chapter 10, more transportation problems, and in this section we are considering so-called assignment problem. And the assignment problems are actually almost special cases of transportation problems. It's maybe not completely clear, but I hope it should become clear very soon. So what is an assignment problem? In an assignment problem we have number of, say, machines, a number of works, it's the same number, and we have to assign for each, let's have 5 of them machines and 5 works. We have to assign them one-to-one somehow. Okay, so this is one-to-one assignment. Let's have an example to illustrate these problems, and this example or problem 10.5 is such. It's called Gola production here. So we have a Kleilaksu master Skytail, and he needs to build 4 different types of Golas in 4 different types of axolotl tanks. And each tank can produce almost each type of Golas except tank 1. Tank 1 cannot produce Golas number 4 or type 4. And each axolotl tank has different setup time for different Golas, and the setup times for tanks and Golas are given in a table like this. So here the minus sign means that tank 1 cannot produce Gola 4, and this 8, for example, means that if we want to assign tank 1 to produce Gola 3, it will take 8 units, say minutes, to set up. And the master Skytail wants to minimize the total setup time, and the question is what should master Skytail do? And if you want, if you think about it a while, it turns out that this assignment problem, it's actually a transportation problem with equal amounts of ports and markets. So ports are the tanks and markets are the Golas, or the other way around. This is symmetric. And the demands and supplies for each port and each market are 1. And that's it basically. If you think about it, you will have a transportation problem. You can also start modeling this by using algorithm 5.2. Remember the algorithm 5.2. So the first step is to find the decision variables. The second step is to find the objective function, and the final step number 3, is to find the constraints. And here actually the trick, as in transportation problems typically, is to find the decision variables. Once that is done, then everything else is relatively easy. And the trick here is to use so-called binary variables. So binary means either 0 or 1. And how do we do it? So we make a decision variable. Again, it will be a matrix, and xij will tell whether a machine I, or here tank I, is assigned to produce Gola j. So xij is either 0 or 1. It's 1 if tank I is assigned to meet the demands, or that is to produce Gola j, and 0 otherwise. So if tank I is not assigned to produce Gola number j. And then once we have decision variables, the objective, it's almost trivial now. There is a big small hiccup here. So here is a total setup time. So this is 14 times x11, 5 times x12, and so on. So they come from this table, of course. So objective function comes from these setup times. So we want to minimize the setup times or costs. So this will be the matrix C associated with the decision variables x, xij. So these are cij's. Okay, so there is this minus sign saying that tank 1 cannot be assigned to goal 4. So x1 4 must be 0, not 1. And how do we do that? Well, we have seen this before. This is the big M trick. So we will make this x1 4, the cost c1 4 associated with that, a big number, very big number. Let's call it a big M. So this is the big M trick. So we choose this to be a very big number, something like 10 or 100 times all the other numbers that there are. So in the solution, x14 is then obviously or must be 0. So this is the big M trick. We have seen this big M tricks before. Then we have this algorithm 5.2, step 3, the constraints. And well, we have two types of constraints. We have supply side. Supply side means that each axolotl tank is assigned to a goal. Each axolotl tank does something. So it means that we have ones here. So the first row says tank 1 is assigned to 1 or 2 or 3 or 4. These are the goalers. This is 1. So in the end, this means that one of these is 1 and others are zeros. And same for tank 2, tank 3 and tank 4. Then we have the demand side, the same thing, but now this is kind of transposed this. So for example, in the last row here we have that goal 4, either tank 1 is producing goal 4, tank 2, tank 3 or tank 4 is producing goal number 4. This equals 1. And putting all this together, so here we have almost an LP. So minimizing Z, so this is total setup time. Constraints that all the tanks are assigned. These are the supply side constraints, and then the demand side constraints. All the goalers are produced by some tank. And then now this is why we are not completely looking at an LP or linear program. So the decision variables are not continuous. They are not just non-negative. They are binary, either zeros or ones. So this looks otherwise good, but this looks bad. And now a piece of mathematical theory. I'm not going to prove anything. I will just state a fact. So the structure of this problem is such that if I relax these conditions, I assume not that they are zeros or ones, but they are just non-negative. So I assume less. So this means that I'm looking at relaxation, and I'm actually looking at the LP relaxation, meaning that if these binary constraints are relaxed to be non-negative constraints, then I'm looking at an LP, and it turns out, it can be proven, that this LP relaxation and this original binary program, they have the same solution. So this means that we can forget these binary constraints and instead look at the sign constraints. So this is the LP relaxation here of this binary integer program here. So only thing that's different is that we are not assuming these decision variables to be binary, we assume them to be non-negative. Then maybe a final step that is not completely needed, but we wanted to look at the supply side to be inequalities less than equal, and demand side the inequalities to be inequalities greater than equal. And if you think about just a little bit this problem and this problem, you notice that they are the same, because this cannot certainly be 0, that's prohibited, and here neither they can be bigger than 1. So these equalities and these inequalities don't change the problem. It's the same problem anyway. And now this is a transportation problem. So we have a objective function that is some I over some j, cij, xij. This is what it is. And here we have a supply side upper bounds. All the upper bounds are 1s. Here we have a demand side with lower bounds. All the lower bounds are 1s. Sign constraints. Everything fits into a transportation problem. Okay, I haven't solved this problem. The solution will be the exercise 10.9 cola production. So solve the problem 10.5. So this was the problem of cola production. And how do you solve it? Okay, you can solve it many ways, but what I'm here looking at is the solution where you look at the 10.8 and notice that this is a transportation problem, so you can solve it by using TransSolver. It should be straightforward. Only small hiccup is the big M here, so you have to define this big M to be something. Well, choose it big enough so that x14 will be 0 in the solution. Well, since the numbers are something like 14 is the biggest number here, it seems, so M100 should do it. That's just a rule of thumb. And finally, there is an exercise 10.10 called S-Solver. Sorry about the name, maybe not a very beautiful one. So this is for those who are experienced in programming. This should be very easy for those of you. So you should make an S-Solver that takes in the data of an assignment problem. So the data is just an assignment table, so the table of the setup costs, and then returns the optimal schedule. And if you start from scratch, this is probably very tedious and difficult to do, but now, since we already have this TransSolver and way of understanding assignment problems as transportation problems, it's actually relatively easy to build this function as solver. You just make a wrapper for the TransSolver where you just set the supplies and demands what they should be, that is once, and then call TransSolver with the appropriate parameters. That's all for more transportation problems, and in the next videos we something completely different. Bye.